Hello, hello.
Are you able to get my voice?
Yes, good afternoon, guys. Just wait for 5 minutes, we'll start. So have you revised all the points which we have discussed yesterday? So very important subject. Try to spend little time here itself. When we are taking the subject, on the same day you try to revise it. Then it becomes easier for you because time is not much. Try to make advantage of it. Right, shall we start? Yeah, it's time now, 2 o'clock. We'll start now, okay? right? So yesterday we discussed about these points. What are the properties of different network elements? R, L, and C we have seen. Resistor, linear bilateral, 100% passive. Inductor, linear bilateral. It may be active or it may be passive, depending on the power you get. Product of voltage and current, if it is negative, it is behaving as active. If it is positive, it is behaving as passive. Similarly, same rule for capacitor also. So we have seen one problem, RL circuit with DC source as well as RC circuit with DC source with switching actions. So initially we kept the source. After inductor or capacitor saturates, we removed the source, and we have discussed current characteristics and voltage characteristics on capacitive branch yesterday, and confirmed where it is active and where it is passive. So these are all the points we have discussed. Very three important network elements, R, L, and C. Now let us see simple questions that have come in GATE exams and other competitive exams. This is the first one. Right. So here you need to identify the nature of network element. What is nature of network element in this graph? Means you have to confirm whether it is linear, non-linear, active, passive, unilateral or bilateral, right? Now tell me whether first it is linear or non-linear. What I told, if the input output characteristic graph of a network element is a straight line passing through origin, then it becomes linear. Otherwise it is non-linear. This is one way. If you are given in terms of expression, check for additive principle and homogeneity principle. Sum of inputs should give sum of outputs. Input multiplied by constant k, output also should be multiplied by the same constant k. So here you are given graph, very simple. It is not a straight line passing through origin. This is not at all a straight line passing through origin. So definitely this network element is non-linear, no doubt. Okay, we can confirm it. Now, is it a active element or passive element? What is the condition of active elements and passive elements? How we can confirm whether the network element is active or passive? So what I told, if you take a product of current and voltage, if the product happens to be negative, then it is active. If the product happens to be positive, then it is passive. So you can see in the graph, in the first coordinate, product of V and I are positive. But in the second coordinate, product of V and I is negative. Means what is the meaning? Sometimes it is active and sometimes it is passive. But even though at a single point of time, if the product happens to be negative, definitely you can confirm that the network element is active only. You have to consider it as active. Even at one point of time, it is able to deliver. So we have to consider it as active element. So this is network element which is active. Now third one, is it unilateral or bilateral? So what is the condition for unilateral and bilateral? The network element should behave in same manner for both the directions of flow of current. That means what is the meaning? The ratio of voltage to current should be same in any coordinate you take, or image of coordinates should be there. That means suppose if you say some I1 and some V1. So this coordinate is located somewhere here. Okay, this is some value of V1 I1 coordinate. The image of that V1 I1 means what? It will be minus I1 minus Y1 minus V1. It will come somewhere here. But is this coordinate on the axis? It is not there. It is actually in first and second coordinate. That means this is a unilateral network element. That's all. Very simple method of identifications. Just follow the technique I have given. Input output characteristic graph, straight line passing through origin, linear. First point. Second point, product of voltage and current, if at all anywhere it becomes negative, confirm it as active, otherwise passive. If image of each point is present on the graph, image means what? V1 I1 image will be minus V1 minus I1. That means negative of whatever the quantities they have given. Image of first coordinate should be third, image of second coordinate should be fourth. That means graph should be symmetrical in 1, 3 and 2, 4. If such characteristics are happening, then it is bilateral, otherwise it is unilateral. So just apply these rules, you will get the nature of the network element. Very simple way of identifying the nature of network element. I hope it is clear. Are you getting me? Okay. Right. Let us see one more. Same model. This network element. What are the properties of this network element? First tell me, is it linear or non-linear? It is not a straight line passing through origin. After going sometimes it has got saturated. Here. This is coming here. Similarly, here also it is coming like this. So definitely it is non-linear, no doubt. Okay. Second one, is it active or is it passive? You can see product of voltage and current in first coordinate is always positive, and product of voltage and current in the third coordinate is also positive, because you are multiplying negative current with negative voltage, so the result will be always positive. So definitely you can confirm that this network element is passive. Okay. Third one, is it unilateral or bilateral? Image of first coordinate is 3, image of second coordinate is 4. So if you take observe very carefully, you might make a mistake here. In the third coordinate he did not give you -5, he gave you -3. If this would have been -5, then you would have gone for bilateral, but it is not bilateral. You can see the characteristics are different. First coordinate it is different and third coordinate it is different. So it is not symmetrical. It is not symmetrical in first and third quadrants. Therefore, this network element is unilateral. That's all. Is it clear now? If instead of -3 it would have given us -5, then definitely it would have become bilateral. But it is not bilateral, it is unilateral. Simple questions. These questions are asked in different exams for 1 mark. Time bounded exams. 1 mark, 1 question. And 1 minute maximum. So many are giving answer as a bilateral. Be very careful. It is not bilateral. It is unilateral. Okay. Right. Let me go to the next one. This is also same model. Now tell me, what are the properties? Is it a straight line passing through origin or not? Definitely, you can see it's a straight line passing through origin covering second coordinate and fourth coordinate. So definitely network element is linear. We are saying because graph is straight line passing through origin. Next. Now, is it active or passive? You can see here product of voltage and current in second coordinate is negative, as well as product of voltage and current in fourth coordinate is also negative. One quantity is positive, another quantity is negative. So definitely you can confirm it is an active network element. Third point, is it unilateral or bilateral? You can see image of second coordinate is fourth coordinate. Image of second quadrant is fourth coordinate. So exact graph is there in second and fourth coordinate, replica. Whatever that is there in second coordinate, The same is there in fourth coordinate. Therefore, network element is bilateral. That's all. So definitely this element is a bilateral network element. Is it clear? Right. Okay. So these type of questions are very simple. You need not spend more time. Just to give importance these properties how we are discussing. Use them and get the answer immediate. Within seconds you have to go for this. Right. Now let's do some more bits. This is a question given in engineering services prelims paper. See this question. It's a very good question. So here the voltage and current characteristics of an element is shown in the figure. So first one which he has given is voltage versus time. Second one is current versus time. So this is the graph given to you. Okay. Voltage versus current characteristics. Voltage and current characteristics of an element is shown in the figure. So first waveform is like a ramp function. Second waveform is like an exponential function, increasing exponential. The nature and value of the element are dash. What is the element and what is its value? Is it inductor or is it capacitor basically? How you can tell? Now how you can identify? First one is voltage, second one is current. Now is current integral of voltage or current derivative of voltage? If you integrate ramp functions, you will get parabolic functions. Integration of ramp functions gives parabolic functions. This is a clue here. That means what is the meaning? The value of current which you are having is obtained by taking a integral of voltage. Means what should be the network element? Definitely it should be inductor or not, because voltage we have as derivative of current. So what will be the current? It will be integral of voltage 1 by L into V of t dt. Is it clear? We have a relation VL of t equal to L into d by dt of IL of t. So from here what is IL of t? It will be 1 by L into integral VL of t dt. That's all. So definitely the given element is inductor. So either your option should be D or your option should be B. Either one of these should be correct. Okay. Now integration limits will be starting from 0 because both the waveforms are started at 0, and upper limit will be t up to present state. Okay. Now my requirement is to find the value of L. You have to find L. That is what is the expression. Now what is this VL of t expression? This coordinates you take, starting point is 0 0, and the coordinate which he has given is x is 2, y is 20. So what is the slope? It becomes 10. So what is your line equation? VL of t will be equal to 10t. Okay. So what will be my IL of t? You can take IL of t at any point, either at 1 second or 2 seconds, because only those two values are given to you. You can observe here. The value of current IL of t is given at 1 second and again given at 2 seconds. So you express at any one point. What I am doing is I am taking at t equal to 1 second. What will be the values? IL of t at t equal to 1 second is 2 amps equal to 1 by L. L we have to identify. Integral. So I am calculating up to 2 seconds. So integral limit will be from 0 to 2. Okay. Sorry, 0 to 1. Because I am taking my current output at 1 second. So you have to take your upper limit as 1. Okay. Into what is VL of t? VL of t is 10t dt. That's all. That means what you will get? 2 into L, you will get it as 10 you can bring outside, integral of t will be t square by 2. So you will get 5. So value of L will be 2.5 Henry. That's all. So what will be your correct choice? Option B. It is inductor and its value is 2.5 Henry. So these type of questions are coming in competitive exams for 1 mark. They are not complicated. They are quite simple. Yeah. Okay. So just to use the same topic, these topics we have discussed. That's the reason I have told all the equations. I have derived them clearly so that you don't memorize, just understand first. Then automatically you can develop these points. Is it clear? Shall we go on to the next question? I'll just stay for some 10 seconds. If you have anything, just let me know. First point you have to observe here is voltage curve and current curve. Current curve is parabolic function, voltage curve is ramp function. So what is the relation between ramp and parabola? When you integrate ramp, you will get parabola. That means current is expressed as integral of voltage. So that is the reason we are confirming that the network element is inductor, because this is the relation we have on current and voltage on inductor. So from here, if I write current, it is 1 by L integral of voltage. So definitely it is satisfying my condition, because voltage function, if you substitute as ramp, current function I am getting as parabola. So it is inductor fixed. What is the value? You take current on an inductor either at 1 or 2 seconds, because only at these 2 points you are given y-axis. So I am taking it 1. So current on inductor at 1 second is 2. U is equal to L, we don't know, we have to find. Limit of integral, starting point will be 0, because there is nothing given before 0. Upper limit, whatever the value of time you are taking here. So I am substituting upper limit as 1. And expression for voltage on inductor is a 10t. Slope is 10. Get the line equation. Substitute here. Just perform integration. You will get here. That's all. A simple numerical, not complicated. You can do within 1 minute. Right? Right. Okay. Let's go to the next problem. This one. This is also a very good question given in ISRO paper. For the RL circuit shown in the figure, please see, I am discussing this question. For the RL circuit shown, the current I of t for unit step voltage will rise to 0.63 in dash. How many seconds? So be very careful here. Question is a little bit twisted. It is not very much direct. ISRO papers, these type of questions are very common. You have to be very careful. So first understand here, what is the source he is telling? Source is U of t. U of t means what? It is 1 volt for all values of t greater than 0. That is about your source. Connected with inductor, whose value is 1 Henry. There is no initial value of current on inductor. He did not tell anything. So before source, there is no value of current that is stored on inductor. Initial value is 0. Okay. And then you have this 2 ohms resistor connected in a series. That's all. So this is a circuit you have. Now, the direction of the current, he only gave it. He has given as I1 of t. So let this be I1 of t. Okay. So what is he asking? The current I1 of t, this is I1 of t only. Don't worry about I of t and I1 of t. I think it is I1 of t only. Okay. The current I1 of t for unit step input voltage will rise to 0.63 in dash. What is that 0.63? What is the meaning in the question is I1 of t at t equal to some t1 must be equal to 0.63 of final value. This is very, very important observation there. 0.63 means don't think it is 0.63 amps. He did not tell that amps there. See carefully. It will rise to 63%. Should be the exact question actually. But instead of giving you 63%, he just gave 0.63. That's all. 63% of which value? Initial value or final value? Final value. How you will tell? Because inductor curves will be rising. When you connect with a DC source, when steady state occurs, what will happen? Inductor becomes short. Then you will have a constant current flowing in the circuit. That means it takes some time to reach a steady state. So which time you have to consider? You have to consider the time where inductor is reaching steady state, means 63% of final value. So that is what is meant by 0.63 here. I hope it is clear. Okay. Now simplify this. Just to convert into S plane, this becomes 1 by S. This becomes S into L. S. This remains as 2. This current becomes I1 of S. Okay. Now just write a closed mesh equation. So when current is flowing in this direction, this should be plus, minus, this should be plus, minus. Already this is minus and plus, right? So go in the given closed mesh. If current goes from negative to positive, treat it as positive voltage. Current goes from positive to negative, treat it as negative voltage. Add all the voltages and equate with 0. So what will happen? 1 by S minus S into I1 of S, impedance multiplied by current is voltage, minus 2 into I1 of S equal to 0. That's all. Over. Okay. So what will be I1 of S here? I1 of S, you will get it as 1 by S into S plus 2. Okay. So how you can write this? We can write this as A by S plus B by S plus 2. So you will get a value as 0.5 and B value as minus 0.5. Okay. So I am having a I1 of S as 0.5 by S minus 0.5 by S plus 2. So what is my I1 of T? 0.5 I can take common and express as 1 minus e power minus 2t amps for t greater than 0. Simple. Okay. Now what is the requirement he is asking? He is saying I1 of t at some time value t equal to t1 has to be 63% of final value. 63% of final value. Final value is how much? Substitute t tends to infinite, e power minus infinite will become 0. Remaining term is only 0.5. So that means it is 0.63 divided by 2. That's all. 0.5 I am writing as 1 by 2 over. That means 0.5 into 1 minus e power minus 2 into t1 is equated with 0.63 divided by 2. That's all. So 2 it will come on the left side. It becomes 1. So you will have 1 minus 0.63. So it becomes 0.37 equal to e power minus 2 into t1. Take natural logarithm on both sides and find value of t1. Do you get my point or not? Yeah, most of you got a 0.5. So it will be approximately 0.495 seconds. So you can equate it with 0.5 seconds. Okay. So your correct choice will be option C. You may think that this concept is from transients. Actually, transients also use the same concept. Time taken by the response to reach 63% of final value is one time constant, L by R. We will see these points a little later when we are dealing with transients. But not necessarily in every time you will get 0.63 only. He may ask 0.45. Then this is the standard procedure. That's the reason give importance to standard procedures. For any one value, you can remember formulas, but all questions you cannot do. That's the reason go for the standard procedure. Important point in this question is 0.63 only. Generally, what you will do is after getting the equation, you will equate with 0.63. You will never get answer. 0.63 here represents 63% of final value. That is what is very, very important. If you get that point, then that's good. My work is done. That is why I have taken this question, just to understand that point. Right? Shall I go for the next one? Final value is 1 by 2. That's the reason I have divided with 2. Some guys are asking why you divided with 2. Clear? Here I have divided with 2 because final value is 0.5 amps, 1 by 2. So you will get this answer as 0.5 seconds. Okay? Right. Let me go for one more question. See this question. Figure shows the current flowing through a capacitor. So actually he has given IC of t as a function of time, current flowing through a capacitor. Determine the charge acquired by the capacitor up to first 5 microseconds. So what is the relation between charge and current? Rate of flow of charge carriers is nothing but current. That means IC of t will be d by dt of QC of t. So charge accumulated on capacitor will be integral of current flowing on a capacitor. Now what is he asking? Charge accumulated up to first 5 microseconds. So lower limit is minus infinite. Minus infinite means starting point of the graph. Starting point is 0. Upper limit from where he is asking, up to where? He is asking up to 5 micro. So take upper limit as 5 micro. That's all. Now don't waste your time in taking line equations. Okay, that is correct process only, but it will take more time. Whenever you have such type of graphs, especially given in competitive exams, time bounded exams, integral of a function is nothing but area of the function. Remember that. Taking integral on a signal is nothing but finding the area under that signal. So you just take the area up to 6 microseconds, sorry, up to 5 microseconds. That's all. Your work is done. So your 5 microseconds will be somewhere here. Middle. So you can simply divide this into standard waveforms. First waveform I am dividing into triangle. This one, this blue one. So what is this area of the triangle? Let us assume this is the first one. What is the area of this triangle? Half into base 3 micro, height 5. So it becomes a 15 by 2, 7.5 microcoulombs. Finish. This is first part. Okay. Next, I am splitting this as one rectangle. Okay. Now what is the area under this rectangle? This will be base into height. Base is 1 micro. Height is 3. So this value becomes 3 microcoulombs. Finished. Next, this small triangle is there. I'll use one more color. This small triangle, this part. So what is the area of this triangle? It is again half into base. Base is again 1 micro. Height. Height will be 5 minus 3, 2. So this becomes a 1 microcoulomb. Okay. Next. Again, I am dividing this into one rectangle. Up to 5 seconds only he asked, 5 microseconds. So you can take from 4 to 5 microseconds. Actually, you can take as one triangle, but I have split it into two triangles. Let it be not an issue. 4 to 5. So what will be the area under this rectangle? This is base into height. Base is 1 micro and height is 3. So it also becomes 3 microcoulombs. That's all. And one more small triangle is there here. This part. I will take black. So this part. Okay. Now what is the area under this triangle? It should be half into base is 1 micro, height is the exact midpoint of 3 and 5, so it must become 4. Sorry, between 3 and 5. Total height is 2 between 3 and 5, but it is exactly middle value. So that height, whatever you are writing, is actually, see this carefully, half into base is 1 microcoulomb. Height, what is the height that you are getting for this particular triangle? The small one, this area only. I want only this portion. Up to this is 3 and this is 4. So the difference of these two heights is 1. So you will get a 0.5 microcoulombs. That's all. Okay. So what is your answer now? So the total charge accumulated on capacitor QC of T will be up to 5 microcoulombs. Just add all these values. 0.5 plus 7.5 becomes 8, plus 6 becomes 14, plus 1 becomes 15. So your answer will be 15 microcoulombs. That's all. So this will be your right choice. Very simple. Just use standard pictures and do the answer. Don't complicate the question by taking line equations. So total charge accumulated on capacitor up to first 5 microcoulombs is 15, up to first 5 microseconds is 15 microcoulombs. Very good. Right. So these are some questions which came in competitive exams, direct questions only, not complicated. Just that one question which you have done previously, that inductor, 2 questions. Those 2 questions are little bit different. So you have to take care of those parts. But otherwise, topic is very, very simple, not at all complicated. Okay, right. Now let us see the remaining network elements. We have seen R, L and C, which are 3 important network elements. Other network elements we have are sources. What are the different type of sources that we can use in network theory? Okay, see this part also. This is also a part of network elements only. 3 network elements we have seen, R, L and C. We will see the remaining elements. I am classifying them as sources. Now sources, you are having a broadly classification as 2 parts. One are called as ideal sources and another one are called as practical sources. Under ideal sources, again we have ideal voltage source and again we have ideal current source. IVS is ideal voltage source, ICS is ideal current source. Under practical sources, broadly classification, again we have 2 parts. One are called as independent sources and another one is called as dependent sources. Again under independent sources, we have voltage source and current source. And dependent sources, we have 4 categories: voltage controlled voltage source, voltage controlled current source, current controlled voltage source, and current controlled current source. These are the 4 dependent sources. So throughout our networks, we will come across different types of questions with these type of sources. Okay, except this, no more sources are there in the circuit. Only these type of sources are present in the circuit. Ideal, practical. Under ideal, ideal voltage source, ideal current source. Under practical, independent sources and dependent sources. Independent voltage source, independent current source. And dependent sources, voltage controlled voltage source, voltage controlled current source, current controlled voltage source, and current controlled current source. Okay. Now let us see briefly about these sources, what these sources exactly mean to us. Now first let us see ideal voltage source. Ideal voltage source. Now, when you talk about ideal voltage source, keep in your mind the internal resistance, which is represented as RIN, is 0. Internal resistance is always 0. Whenever we come across this term of internal resistance means it is not connected from outside. It is present within the device due to some manufacturing defects or due to the property of the material, whatever it might be. The resistance that comes into picture for that particular device, we call it as internal resistance. Every device will have its internal resistance, no doubt. But ideal means what? Ideal means, strictly speaking, that does not exist. It is only for theory purpose. So when you take an ideal voltage source, its internal resistance is considered as 0. So I told 2-3 times in yesterday's class also, whenever you take any branch, if you are connecting with voltage sources, we connect in series. If you are connecting with current sources, we connect in parallel. Same logic you apply here. So I am taking an ideal voltage source. Let us assume ideal voltage source value is Vs. So internal resistance, if something is there, it should be connected in series. But because internal resistance is 0, it is like short circuit. So you need not connect anything. So this part of the circuit which we are calling is called as source. On the left side of these terminals, A and B. Okay. Now, right side of the terminals will have something called as load. Load means consuming. Any branch that consumes power delivered from the source is called as load. So this right side part of your network is called as load end, or simply we call it as load. Okay. Now let us assume some current IS is delivered by the source. So when I say delivered by the source, current should flow from negative to positive. So it is flowing in this direction. Now there is no other path. Current should come on resistor here. So it is IS. So when current is flowing on load, which is consuming power, it is absorbing, means this should be plus and this should be minus. Now let this value of voltage be some V here. This is how we give the conventions when you take any question. Observe these points carefully. Okay. Now if you write one simple mesh equation in this closed mesh, what is the mesh equation? You are going through negative to positive, so it is Vs minus voltage on that branch is Is into RL equal to 0. Current multiplied by resistance. So value of Vs is equal to Is into RL, which you can also call it as VL. That means what is the meaning? The entire voltage that is there on the source is delivered to the load. There is no wastage at all. So these type of sources are called as ideal voltage sources. Their internal resistance is 0. Practically, there is no existence of an ideal voltage source. Only for theory part we study this. Is it clear? And I am telling in classroom, I can see your faces. But now I can't see your faces. Nothing is there. So I am assuming that you are understanding. That's the reason I am going quite slow also. Okay. Right. Right. Is it clear? Now. Next. Now, what do you mean by practical voltage source or simply a voltage source? Practical voltage source. Or simply normally we call it as a voltage source, that's all. If you call voltage source, the meaning is it's practical only. So here the value of internal resistance is not 0. It will have some value. Some value should be there. It is not 0. Okay. So I am taking a practical voltage source whose magnitude is Vs. Because it's an active source, it should deliver some current. So it is delivering current Is. So I am taking the direction of current from negative to positive. Now internal resistance is not 0. So I am connecting some RIN in series. Be very careful. This is not the one which I am connecting externally. This is coming because of a device operation only. Don't think I am connecting it. Okay. That is what is meant by internal resistance. Now these are my terminals A and B. So left side of this terminals is nothing but source end or source terminals. Now, right side, I am connecting the same load, whatever I have connected previously, RL. Now, because of this current is flowing, you can mark the directions plus, minus, same current comes here. So plus, minus, and voltage let it be equal to VL. And this side of the circuit is called as load end. Okay. Clear? Right. Now, what is your mesh equation? If you write the mesh equation in clockwise direction, what will be your mesh equation? Same, Vs minus, now this figure will come, Rin into Is minus RL into Is equal to 0. So from here, I can express Vs as, how you can write a Vs value? As Rin into Is plus RL into Is, I am writing as VL. Voltage on load is current on load multiplied by resistance of load. So you can express VL as Vs minus Rin into Is. So previously what we got? We got a value of Vs and VL both same. Means whatever that voltage source is there, it will deliver entire power to load. But now what is happening? The value of VL which you are getting here is definitely less than Vs. Some part is wasted. Now tell me, if you want a practical voltage source to have as much as less wastage as possible, means it should not be the case where a lot of power is being wasted internally. It should be having as less power wastage as possible. What should be the value of RIN? Will you take it high or will you take it less? This figure must be very much close to 0. You cannot make Is 0. Is cannot become 0. Is will be standard. So RIN should be kept as low as possible. So RIN is not 0, but RIN is very, very small. You have to see that it becomes very small. Generally, it will be from 3 to 5 ohms. That is practically allowed values for practical voltage sources. So you can see this you just buy 5 volts batteries. Okay, you don't use them. Let us assume you bought them, removed the cover, keep it like that for 2 to 3 years, at least some 6 months. 6 months is quite enough. So initially when you test it, it will be 5 volts. It will not show 4.9599. It will show like that. But after 6 months, if you see, it will show somewhere around 3.5. So where is that 1 volt gone? You did not connect any load. Suppose if you have used in some watches or some TV remote or any AC remote, if you use it will automatically reduce. But without using how that voltage has come down, that is because of this internal resistance only. It will create a closed path and it will keep on reducing your voltage very, very slowly. Every day some microvolt will decrease. By the time 6 months or 1 year happens, you will see half of the voltage will be drained out. So that's the reason whenever you see batteries, it will never show full voltage. When you buy, it will show almost close to 5 volts. But after 1 year or 2 years, if you don't use and keep it as it is, then it will show you at least half of the voltage. So the logic there is internal resistance. So if you keep that internal resistance very, very small, what will happen? The life of the battery will be for more time. If it is high, then automatically, even if you don't use it, will come down. That is the difference between Duracell batteries and normal other companies like Everyday batteries. Why we buy Duracell? Manufacturing procedures. Their manufacturing procedures are such a way that internal resistance is very, very small. So the life of the battery will be for more time. That is the only case. Even though they are electrolytic batteries, the concept of this internal resistance is always same. So that is what is meant by internal resistance to be kept as small as possible for all practical voltage sources. Okay, right. Let me go for the next one. Now let us see what is ideal current source. What is an ideal current source? So when you talk about an ideal current source, internal resistance is infinite, very high in mega ohms. So we take it as an ideal case as infinite. Okay, ideal case means they don't exist, only theory purpose. That's the reason infinite does not exist, but theory part we consider as infinite. So it's very high. Now I'm taking an ideal current source. So let the amplitude of the current source be Is. Now because this is a delivering current source, I am taking a representation of voltage such that current comes from negative to positive. Let us assume this is some Vs. Now I told any branch when you are connecting with current source, it should be connected in a parallel. So because internal resistance is infinite, it's a like open circuit. You need not connect any branch. So you leave it as open. Now these are our terminals A and B. Okay. Now I am keeping my load as it is, which is equal to RL. Now what will happen to this current Is? When the current Is comes to this point, there is open circuit path here. So on open circuit, you cannot see any current. The same current will come here and flow across RL. So when current flowing on a resistor, it is passive plus minus, let the value of voltage divided by VL. So what is the relation between IL and IS? Let the current flowing on this load resistor be IL for understanding purpose. So what is the relation between IL and IS? Definitely the value of the current flowing on load is the value of the current delivered by source. That means there is no wastage at all. So when this condition exists, then we say that this is representing an ideal current source. Internal resistance, ideal case is infinite. That is the meaning of an ideal current source. Right? Is it clear? Okay. Now, what is the meaning of a practical current source or simply a current source? So when you take a practical current source, the value of RIN is not infinite. It will have some practical value. What should be that value? Now, when you take a practical current source, so I am taking again current source amplitude as Is, because it is delivering, let us assume voltage on it is Vs, negative to positive. Now, this RIN should be connected in a parallel. So I am keeping one internal resistance in parallel with the current source. And you are having the same load resistance RL as it is. Okay. Now, these are our terminals A and B. So left side part is the source end and right side part is a load end. Now what is going to happen? Now if you see, all these branches are connected between two set of nodes. So whenever network elements are connected between same set of nodes, the elements are said to be in a parallel. Same current flows on two branches, they are in series. If network elements or any branches connected between same set of nodes, then they are said to be in parallel. So they will have same voltage but different currents. Because I have referred this voltage as Vs, same voltage will be there also on RL, and the same voltage will also be there on RIL. Same voltages will be there. Now for a resistor, current should flow from positive to negative. So this should be the direction of current on RIN, and this should be the direction of current on RL. Here Is is coming like this. So if I represent this node, say this node is some n. What is the nodal equation at the node n? We can write. What is mean by nodal equation? Sum of all the currents at a node is 0. Sum of all currents at a node is equal to 0. Simple technique. Just like sum of voltages in a closed mesh is equal to 0 for KVL, sum of all the currents at a node is equal to 0 for a KCL. So here we use KCL. Series circuits we use KVL, parallel circuits we use KCL. Simple logic, nodal analysis and mesh analysis. So here when you write a nodal equation, keep this in mind. If the current comes towards node, current towards node, take the current as negative. If the current goes away from the node, take that value of current as positive. That's all. Simple technique. Current is coming towards the node, take it as negative. Current is going away from the node, take it as positive. Add all the currents at a node and equate it with 0. You will get a nodal equation. So what is happening in this particular case? Is is the current that is coming towards the node. So take it as minus. Current flowing on this RIN is how much? It is flowing away. So first write plus. What is the current flowing? Current is voltage by resistance. So Vs divided by RIN. And current on RL is also going away. So first write plus. Let this current be equal to IL, equal to 0. That's all. The current flowing on this branch I am taking as IL. So from here what is IL? It is exactly equal to IS minus Vs by RIN. So whatever the value you are getting, this value of IL is definitely less than IS. No doubt on that. That means definitely it is not an ideal case. It's a practical case. Now, if you want the maximum current to be flowing on the load delivered by the source, what is the appropriate value of RIN will you take? Will you take it a high value or will you take it as a low value? The second term should be as small as possible. So Vs cannot be changed, it is fixed. So take RIN as maximum as possible. That means the value of RIN will be in mega ohms. Generally we take it in mega ohms, 5 mega ohms, 10 mega ohms, whatever it is. So that current will be very, very small and most of the current will be delivered to the load by the source. So this is what happens when you take practical current sources. Is it clear? So internal resistance for ideal voltage source is 0. Internal resistance for ideal current source is infinite. Practical voltage source internal resistance should be very, very small. It should be in ohms, maximum from 3 to 5 ohms. And internal resistance for practical current source should be very, very high. It should be in mega ohms. So this is the criteria we require when we are dealing with ideal sources and practical sources. Is it clear? So practical also we have a practical voltage source and practical current source. Ideal sources also we are having ideal voltage source and ideal current source. So these are different types of sources which you mostly come across. DC AC is also a classification, but there is no particular methodology to define that. DC means what? Frequency 0. AC means it will have some frequency, that's all. Apart from that there will be no points. So they are considered as sources only. Okay. Is it clear? Now, next is we have dependent sources, very, very dangerous elements. You have to be double careful when you are doing problems on dependent sources. Very, very dangerous elements. Because as the name tells, the behavior of the source is completely controlled by the response coming on any other branch in the network. Okay, that means just take this case. All dependent sources are represented by rhombus symbol, this symbol. Okay, any dependent source. I told 4 dependent sources are there, so you can take any category. This is one case. Suppose if I want to consider it as a voltage source, then I have to write plus minus. So this is some voltage source Vs. Okay, now this becomes a voltage controlled voltage source. What is the meaning here? When I say VCVS, it is called as voltage controlled voltage source. So the value of this voltage source Vs is controlled by the value of the voltage that is present on any other network element X present in the network. So we don't know what is that network element as of now, but on that network element, it will have some voltage. That voltage will be controlling your dependent source. That is most important observation here. That is what is meant by dependent sources. Now, when you say voltage controlled voltage source, magnitude of the voltage source is completely controlled by voltage across any other branch present in the network. That is the meaning of this statement. Now, suppose if I keep the direction like this, Is, what will happen? Or if I change the direction like this, what will happen? What is the meaning here? This is a voltage controlled voltage source fixed. When the current is flowing from negative to positive, that means what is the meaning? Is it active or passive? It is active. So we can confirm now as this is active voltage controlled voltage source. If the current is flowing from positive to negative, then it is a passive. So we can confirm that this is a passive voltage controlled voltage source. That's all. So this is how we can define a dependent source. So one is what is the type of dependent source? Another thing is what is the response that is controlling your dependent source. So based on these 2 points, we have to define a dependent source. They can be both active as well as passive. So how you can confirm? By taking the direction of current as well as voltage. Then only you can confirm whether they are active or passive. Now, if you take next one, let us assume I want to take we have seen voltage control voltage source. I want to see a current control voltage source. That means what is the meaning? It is a voltage source only, same shape. So because it's a voltage source, I can write plus minus. But the amplitude of this voltage source is controlled by current flowing on any other branch in the network. So I am writing as K into Ix. So this magnitude will control your Vs. That is what is meant by current control voltage source. Now again, these can be active as well as passive, just like previous cases. Similarly, what is a voltage controlled current source? VCIS. So here we are talking about a current source. So dependent source diagram is same, symbol is same. But now we are talking about current source. So take a current source like this. Now it is controlled by voltage. That means magnitude of the current source Is is equal to some constant K into Vx. So the current depends on voltage across any other branch present in the network. So this is what is called as voltage controlled current source. Again, they can be active as well as passive. Now last one is current controlled current source, ICIS. So it's a current source, same symbol, and it is controlled by current across any other network branch present in the network, IX. That's all. These can be also active or passive. So these are 4 types of dependent sources we have in our networks. All will have the same shape. By seeing a type of source and the branch which is controlling the source, we can confirm what type of dependent source it is. So this is how we can represent. Okay, they can be both active or passive. Don't think when you see the name as source, they are always active. That is not a strict theory. Only when voltage and current product is positive, then only they are passive. If the product is negative, then only they are active. So use the same logic in whatever the problem you solve. Okay, very, very important observation. Now, practically we can have these examples also. Voltage control voltage sources, best examples are operational amplifiers. Output voltage is completely controlled by some gain parameter into input voltage, correct or not? What are the op-amp equation you write? Output you write it as minus R2 by R1 into input, or you write output voltage as 1 plus RF by R1 into input voltage. Correct or not? So this is one very good example of voltage controlled voltage source only. Output voltage is completely controlled by input voltage by multiplying with a gain factor K. So this is one best example of voltage controlled voltage sources. Now, any other example, like suppose if you take MOSFET, what type of device is this? I mean, in terms of sources, how can you classify MOSFET? First of all, is it controlled by voltage or controlled by current? It is completely controlled by voltage. So it's a current source because the ID will flow from either source to drain or drain to source. So it's a current source completely controlled by gate voltage. So whatever the voltage you give it to gate terminal, based on that voltage, you will have drain current. So MOSFETs are very good examples of voltage controlled current sources. All these are nonlinear devices only. But when they are in active region, you can confirm them as voltage controlled current source. Now, current controlled current source. How can you say whether the source is current and it is also controlled by current? One of the best example is BJT, bipolar junction transistors. Input output characteristic graph, if you see, you will have graph like this. For any configuration, if you take, it may look like this. So what is this value? Output is nothing but voltage, VCE. What are these characteristics you will have? I think the input is VCE and output is IC. Depending on the type of configuration, these will be different values of IE or IB. So what are these values? This is nothing but a current source because you will get current in active region, but controlled by current only. So current controlled current sources. So BJTs are one good examples of current controlled current sources. They are nonlinear elements. They can be considered as active. They are unilateral elements. So MOSFET, if you take, this is nonlinear. You can consider as active because you are having a source characteristics and it is unilateral. MOSFET, definitely nonlinear. It can be active and it is bilateral because source and drain terminals can be exchanged with each other. So it is bilateral. So these are the sources, practical sources that I'm talking about. So these are the different type of sources we have in our network theory. Okay. Okay, right. Is it clear? Try to understand these points carefully. So these are the different sources we have taken. Ideal voltage source, ideal current source, practical voltage source, practical current source, and dependent sources. So just have an idea on all these type of sources. There should not be any doubt later on. Okay. Right. Now, there are devices, we name them as voltmeter and ammeter. ammeters and voltmeters. Don't get confused between these two with sources. That's the reason I am telling here. What are ammeters? First of all, tell me whether these are active devices or passive devices. These are measuring devices, 100% passive, no doubt. Okay. Ammeters measures current and voltmeters measures voltage. Third point, how will you connect ammeters? Ammeters major requirement is to measure current. So on whatever the branch you want to measure current, you will connect ammeter in series with that branch. So series connection will be there. So on whatever the device you want to measure current, you will go to that device or particular element, you will connect this ammeter in series. You will take the range of the ammeter, between what range you want the characteristics, that ammeter which is valid range, you connect in series with that particular branch. So they are always connected in a series. Now when they are connected in series, should the internal resistance of ammeter be small or high? Ammeters should not take more power from the source. Devices can take because you are keeping them, but ammeters are measuring devices. They cannot draw more power from the source. That is the reason the internal resistance ideal case will be zero. Ideal ammeter case, it is zero, but ideal ammeters are not there, only for theory purpose. But RIN practical cases should be very, very small. Very, very small. It will be in sometimes milliohms also if you take high-end ammeters. Okay. Similarly, how will you connect voltmeters? Voltmeters should be connected. Voltmeters are the devices which measure voltage. So whenever you measure voltage, voltage should be measured with respect to open circuit terminals. Then you will get the correct voltage. That's the reason voltmeters will be connected in parallel. Across the branch on which you want to measure the voltage, you connect a voltmeter in parallel. Then you will get the voltage. That's the reason we say open circuit voltage and short circuit current. Open circuit voltage means it will give you maximum drop across the branch. Short circuit current means it gives you the maximum current flowing across that branch with the minimum value of resistance. That is actual meaning. So voltmeter should be always connected in a parallel. Now, what should be the internal resistance of an ideal voltmeter? Voltmeter should not draw any current. It should draw a current which is very, very small. Otherwise, they will also have a capability of drawing current from the source. It should not happen. That's the reason internal resistance ideal case is infinite. They represent open circuit. Very beautiful. You will get maximum voltage. But RIN practical cases should be very, very high in mega ohms. So that they will measure only the drop, but they will not take any current. Current, even though they take, it will be microamps. So that will not be any loss for you. So these are the two devices. Don't confuse between ammeter and current source, voltmeter and voltage source, because ammeters, their representation is like this only, just like a current source, and voltmeter representation also is like a voltage source only. But the important difference is current, if at all there, it flows from positive to negative. Voltage representation, if at all there, it is from plus to minus, like this. So this is how you have to show these elements. These are completely passive elements. So don't get confused between voltmeter and voltage source. Lot of difference is there. One is passive, another one can be active. Second point is internal resistance of voltage source is zero, but for voltmeter it should be infinite. Similarly, current source internal resistance is zero, but if you take current source, internal resistance is infinite or very high, but for ammeters, internal resistance should be almost close to zero or very, very small value. So these are devices which are used for measuring current and voltage, measuring devices. So don't get confused between these symbols and your sources. Is it clear? Okay. So these are our network elements. Mostly when you take any network, and solve, you will get these elements only. There is nothing other than this. Whatever you study, it will be on these only. Okay. So if you take our network family, total network family, whatever it is. So what are the network elements we have studied? So first, sources are voltage and current, and then we are having R, L and C. Along with this, one more element that we did not discuss is M. M is called as mutual inductance. Not mutual. Mutual inductance. This we will study when we are dealing with coupled circuits. And then there are dependent sources. So total network, whatever you take in our coming classes, you will not see anything apart from this. Okay, total network family, you have sources, either voltage or current. They can be DC sources or they can be AC sources. R, L and C, dependent sources and mutual inductance. Okay, so absolute clarity should be there on each network element property. There should not be any doubt here. Okay, very good, right? I hope you guys are following. Now just see this point. When you take this sources, voltage and current, these are like parents. If you compare with the normal family, our families, human families, these are like parents. So what they do, they work very hard. Voltage source is like father, current source is like mother. Both work. Nowadays both are working, both are doing jobs, or even mother don't do job, still she does a lot of work in home, cooking, washing, everything. Okay, so that is why we are made very lazy. Anyhow, both are working only. I have to consider them as working only, father and mother. R is like son. L and C are daughters. Okay, now what happens in every month, first 4 days or 5 days, this R will go to source and ask money, pocket money. Give me money, give me money, I have to spend. So what they will do, they will give money. Correct or not? L and C also will go. They will also go to the source and ask money. Definitely they should give. Nowadays more priority for L and C. So they are getting more money. L and C also will get money. So after getting money, what will happen? Daughters don't spend, they save. Complete saving only, just like inductor and capacitor. They don't spend. They completely save. Some 100 rupees is given, they will save 100 rupees. But what will R do? Immediately on that day only he will spend. He will not even think for next day. Full 100 rupees he will spend on the same day. So complete spending, dissipation. Correct or not? Now what will happen next day? R requires money. But if R goes to VRI, he will kick him. Yesterday only I gave you 100 rupees, what you have done? Again he has to give explanation. That is big problem. So that's the reason what he will do. He will come to L or he will come to C. Correct or not? So what he will do, he will beg, please give me some money. So he will take some 50 rupees from L and 50 rupees from C. If two sisters are there with one son, a very beautiful family, because son will get money from father from two sisters, so he can enjoy a lot. Correct or not? So what is happening? Because of this R only circulation is happening. R is giving circulation from the sources. R is also creating circulation between L. R is also creating circulation between C. L and C, what will happen? They will never spend, right? Some other person R from different family will come and spend on them. Correct or not? Nowadays that thing only happening. L and C don't spend, but some R from other family will come and spend. So they are happy only. But you see, suppose only L and C are there in the family, what will happen? R is not there. Family with two daughters. It's a little bit different model because L and C don't talk with each other. It will be very quiet family. R is there means what will happen? Lot of enjoyment. He will always create problems. He will always make jokes. He does something. It makes more energetic. So what is happening? Because of this R only, this entire circulation is happening. That is why I told R is very important. If R is not there, then L and C are unstable circuits, oscillators. Every time quarreling only. But because of R, he is making the circuit stable. RLC circuits, stable circuits. You will get your entire control systems is dependent on RLC only, second order systems. So sources will be there. We are I. So this is your family, inside family, what I am talking. Now, these dependent sources, they're very dangerous. That's the reason I told her. Whenever you have circuit with dependent sources, be very careful. These are relatives. Very dangerous guys. These people will not stay with you permanently. They will come for one day or half day, and they will come and create some problem and go. What they will do, they will come. They will ask, what is your son doing? Son already failed in 5-6 subjects. So what they will tell, he is studying something. That with that he will not stop. What he will tell, yeah, my daughter got all India 5th rank. Then again this R will get much more torture from the source. That is the reason whenever relatives are there in your house, actually the atmosphere will be very, very calm, because what happens if you talk something no one knows. That's the reason whenever relatives comes to your house, you have to treat them very carefully. You have to offer them coffee, tea, food, everything. Otherwise they will go outside and talk very bad about your family. That's the reason relatives will give more respect. So every time whenever circuits are having these dependent sources, be very careful. They will create lot of problem if you don't take them carefully. So you have to watch them first, what they are doing. Based on that, you have to solve your network. So give very importance to relatives. Dependent sources, be very careful. And this mutual inductance, these are foolish people. These are friends. These are also not part of your family, but everyone will have friends. So one friend will be there, already 4 subjects failed. He will go to a friend whose 6 subjects are failed. What will happen? Next year, complete subjects failed, because both are not studying anything. They will simply watch movies, go outside, spend time. So it is like mutual inductance, where the flux is opposite. There is no understanding between them, or additive flux is there, which will help them to solve it. But if one person fails in 4 subjects, he will go to topper and sit with him for some time and study. What will happen? Topper will be topper only. He may not degrade, but this person, instead of failing in 4 subjects, he may fail in 1 subject only. That means a little bit upgradation. Flux has been added, so that influence will be there. So that is what we call it as mutual inductance. So whenever this mutual inductance is there, it can be advantage or it can be disadvantage. So we have to see where advantage is there and use it. That is like friends. So except that M, all the remaining parts, important aspects we have covered. So this is just like our family only. Don't think bad about me. I'm just taking it as an example, just for you to explain, so that these points will be in your mind whenever you come across this. Nowadays, R, L, and C all are equal only. There is no difference at all. But I saw families with R, L, and C are having more energy levels when compared with only L and C. That's the reason I have quoted that point. But anyhow, it's up to you. I don't take anything negative from my side. I'm always positive person only. So this is a different type of areas that you have to see. So you will have circuits with RL, you have circuits with RC, you will have circuits with RL and C. There is no circuit with only L, only C, only LC. Only LC, we use only oscillators, unstable. So generally what we write RL, we'll never write L and R, or we'll never write CR, or we'll never write CLR. We write always R first. Reason is, it is indicating that the first element that is connected with the source is R. So because R can take any sudden changes in current and voltage, if it can sustain, it will sustain. Otherwise, it will simply burn, creating an open circuit, which will help your L and C not to get damaged. That is the only reason we keep R first in writing these points. The meaning itself is R is representing the first network element after the source that might be connected in series or parallel. That is the meaning of writing this points. Okay, just keep these points in mind. It is helpful. Sometimes you go for interviews, these type of questions are also asked. Why you are writing RL, why not LR? Now, this is the simple answer. Okay, assuming you have understood. I am going to the next page. Okay, right. Very, very important point. Keep this in mind. 2 points we told. Element should be connected in series with a voltage source. Element should be connected in parallel with a voltage source, sorry, current source. These 2 points we have discussed. This is the third important point. What this point says is, if you have independent voltage sources, if at all a requirement comes in solving any question, we can replace by short circuit. So there are some cases like superposition theorem, where you are given a circuit with more than 2 sources. You have to remove a source. So whenever you are removing independent voltage source, you can remove it by a short circuit. So just replace that independent voltage source by short circuit and then proceed for solving your question. Similarly, in a network, if you have independent current sources, then we can replace by open circuit. So if at all you want to remove any independent current source from a network, you can replace it with an open circuit. This is how you can remove independent sources from a network. Without the action of a source, you can calculate especially R equivalents in a circuit. In such cases, we can remove independent voltage sources by replacing them with short circuit and independent current sources by replacing it with an open circuit. Next, fourth point, never replace dependent sources with either short circuit or open circuit. Very, very important point. Just now I told dependent sources are very dangerous. They are like relatives. You cannot beat them. That's the reason if at all you want to remove a dependent source, don't simply remove. Just because you have a dependent voltage source, don't replace it with short. Or just because you have a dependent current source, don't replace it with open. You cannot do that in a circuit. Very, very important. Now, is there any possibility that these can be removed? Okay, I will tell that point also. Suppose let's assume you have a dependent source. Let's assume it's a voltage source, and value of this voltage source is Vs equal to some constant K into Vx. Okay, now this dependent voltage source can be replaced by a short circuit when if value of Vx becomes 0, then value of Vs happens to be 0. That means only in that case it is becoming short. That means dependent voltage sources can be replaced by short circuit only when the branch response which is controlling them becomes 0, because it's a voltage controlled voltage source. If the controlling branch voltage becomes 0, that means there is no control on the source. It's completely lost. That's the reason you are replacing it with a short circuit. Similarly, suppose if you have a current controlled current source, let us take one more case. I am assuming this as a current controlled current source. IC equal to some constant K into Ix. Now, for any reason, if Ix becomes 0, controlling branch response is current. That means this dependent source is completely controlled by current. Ix becomes 0, then the value of Is becomes 0. Current becoming 0 means what? It is an open circuit. So you can replace it with an open circuit. So this is the only way how dependent voltage sources can be replaced by short circuits and dependent current sources can be replaced with open circuits. If this condition exists, if this is not happening, then don't touch dependent sources. Very, very dangerous. Never replace them with short or open. Keep this point in your mind. Very, very important. Is it clear? Okay. So these are our total network elements. There is nothing apart from that except mu. I have discussed every point. Only that m I am going to discuss with coupled circuits. When we go to the last part of the session, then we'll discuss about it. Okay. Just a moment. I'm having some power fluctuation. Just a moment. Just a moment. Right. Okay. Right. Let's go for the next topic. So these are network element fundamentals. Now, network simplification techniques. Different techniques are there. We will see each technique one by one. First network simplification technique is series and parallel combinations. We have, I think, broadly 4: series parallel, delta star star delta, source transformation, and balanced images. These are the 4 network simplification techniques. First hand network simplification techniques. Okay. Generally, a 1 mark bit coming from this area, mostly every time. So first we will see this part. Now, what do you mean by series connection? Just to keep this point in mind, series means if you say 2 network elements are in series, that means they draw same current but different voltage. If 2 network elements are connected in series, then they draw same current but will have different voltage. Okay, so that is the exact meaning of series. Most of you know what is series connections. I need not explain it too high, but there are some strong points which you need to note. So we will concentrate on those points. Okay, is it clear? So if you are saying that current on 2 branches are same, that means the 2 branches are in series. So they will have same current but different voltage. Now, let me take a series connection of resistors. So I am taking an independent voltage source V, which delivers current I. Delivering current means it should be from negative to positive. So from now on, whatever I write, please give importance for symbol representation. Now we are going into network theory. Theory is over. Now problems only. Okay. So try to understand the concepts very clearly. Source delivering current. That is my word. So voltage source delivering current I. Delivering means current should flow from negative to positive. That's all. I am connecting 2 resistors in this fashion, R1 and R2. R1 and R2. Okay. Now, this current, whatever it is there, it will come here. It will also come here. That means same current is flowing on R1 as well as R2. That means these 2 elements are connected in series. Now, when current flows on resistor, it's a passive branch. So it should be plus, this should be minus. So let the voltage developed on this branch be V1. Similarly, the same current I is also flowing on resistor R2, and it will be plus minus because resistors are always passive. Let the voltage developed be V2. So this current is flowing in clockwise direction like this, I. That's all. This is what is called as elements connected in a series. Now, what is the mesh equation that we can write? Simple, write mesh equation. Negative to voltage if you are going, negative to positive terminal if you are going, take the voltage as positive. If you are going through positive and negative terminal, take the voltage as negative. Add all the voltages in a closed mesh and equate it with 0. You will get a mesh equation. So what is this equation now? V minus I into R1 minus I into R2. Voltage is product of current and resistance. So I am writing like this. So you will get V equal to I into R1 plus R2. So what is the meaning of R equivalent here actually? R equivalent is the ratio of voltage to current seen across which terminals? Source terminals. Generally we don't use this word so often. So we are actually measuring R equivalent seen from source terminals. Comedy exams, don't worry, like simple exams will be there, like common PSUs. They don't use this terminal language, but GATE or engineering services, serious examinations, they give importance to terminals. So you have to understand that. R equivalent seen from source terminals. That is what we are interested in. So this value is nothing but ratio of voltage to current. So it happens to be equal to R1 plus R2. Unit is ohms, that's all. So this is how we got R1 plus R2. So if you connect the number of resistors in series across source terminals, then R equivalent will be R1 plus R2 plus so on up to Rn. So this terminal is very important. If you keep these two as terminals, then what will be the R equivalent? R equivalent seen to the right side will be R2 only. There is nothing here. So that's the reason this arrow what you are showing here is very, very important. Across this terminal, you are seeing the network. So when you see the network, what will be the R equivalent? Seen from this side. That is what is meant by R equivalent. Suppose if I keep this arrow instead of right left side, what will happen? R equivalent, is there anything there? It's independent voltage, so simply replace with short circuit, 0. So R equivalent to the left of these two terminals is 0. To the right of these terminals is R1 plus R2. That is the meaning of R equivalent. So be very careful. R equivalent means just don't add elements in series. That's not the correct statement. R equivalent with respect to which terminals? In a normal language, our terminals will be source terminals. If nothing is specified in the question, the meaning is it is with respect to source terminals. So R equivalent will be R1 plus R2 in this case. Now, tell me what is V1? V1 I can express as, V1 is a voltage across resistor R1. So I can express V1 as I into R1. So I can write it as, what is I from here? R equivalent we got R1 plus R2. I we can write as V by R1 plus R2. So I can write V1 as R1 divided by R1 plus R2 into V. Similarly, what is V2? This is I into R2. So I can write V2 as R2 by R1 plus R2 into V. Is it clear or not? Now, this form which I am writing is called as voltage division principle. Very simple and very, very useful in our further classes. What this principle tells is, if you have number of network elements connected in series, if you want to find the voltage across any branch, here I am finding voltage across V1 first. So how you will write the formula directly? That resistance or that impedance divided by equivalent resistance or equivalent impedance seen by the source multiplied by total source voltage. So that's the reason I am writing directly R1 by R1 plus R2 into V. Similarly, if you want to find V2, what is the voltage on resistor R2? First write R2 divided by R equivalent seen by the source multiplied by source voltage V. That's all. So this is what is called as voltage division principle. So we will be using this very frequently in coming classes also. So This is what is exact meaning of voltage division principle. Current will be in series, so elements are in series, current will be same, voltage only will get divided. So this is how voltage division takes place on these branches. Okay, derivations, there is no requirement. Actually I am deriving it just to have a clarity for you. Most of you might be knowing this, so give importance to this voltage division principle here. That is what is my requirement. Now if you take an AC voltage source, intentionally I am taking AC voltage source, so I am saying it is delivering, so current delivered should be from positive to negative, sorry, negative to positive, so it should be I of t. Okay, now I am connecting two inductors in series. Inductors, when you are studying in steady state, better to study with AC source, because for DC source they become short. That's the reason I did not take DC source. Inductors and capacitors, whenever we want to study, we deal with AC source only. Okay, now let this be L1 and let this be L2, and the same current I of t is flowing on both the branches. Let these voltages be V1 of t and V2 of t, and the current flowing in the circuit is I of t. That's all. Is it clear? Now assume that there is no mutual inductance. Generally when inductors are connected in series, some mutual inductance will be there. I am confirming that the value of mutual inductance is 0. Consider M as 0. Okay, now what is the mesh equation we can write here? V of t minus voltage on first inductor is impedance multiplied by current. What is impedance? J omega L1. Current is I of t. Again minus, this is plus minus, current flowing, treat them as passive. Impedance is J omega L2 into I of t equal to 0. So we can write V of t equal to I of t into J omega into L1 plus L2. So this is like J omega L equivalent into I of t. So what is the L equivalent when inductors are connected in series? It will be L1 plus L2. When there is no mutual flux or mutual inductance, then inductors connected in series, it is just like adding individual values. That's all. Okay. Now what is the V1 of t? You can express this as J omega L1 into I of t. So you can write this as L1 by L1 plus L2 into V of t. Similarly, what would be V2 of t? This is L2 by L1 plus L2 into V of t. That's all. So this is what is a voltage division principle applicable on inductors. Same as resistors, there is no change. I want to find the voltage on L1. Take L1, divide it with the L equivalent, multiply it with total source voltage. So your L equivalent is measured seeing across source terminals. Remember that. Just a moment. Right. Just a moment. Right. Okay. So these are inductors connected in a series. Next. Now let me take capacitors connected in series. So I am taking again an AC voltage source which is delivering a current I of t. Series. Let their values be C1 and C2. Let the values of voltages be VC1 and or V1 and V2. Okay. Now the same current I of t will flow on both the branches. So treat them as always passive, plus minus plus minus. So the closed mesh current is I of t. That's all. Okay. Right. So what is the mesh equation now? V of t minus impedance and capacitor is 1 by j omega C1 into current is I of t minus 1 by j omega C2 impedance on second capacitor some technical problem is that my system got shut down, so I could not start. Okay, I'm back. Are you able to get my voice? Yes, guys, let's continue. Okay, right. So here we are going through mesh equation when capacitors are connected in a series. So V of t minus 1 by j omega c1 I of t minus 1 by j omega c2 into I of t is equal to 0. So what will be your V of t? It will be I of t into, you take 1 by j omega common, then you will get 1 by c1 plus 1 by c2. So it is just like a V equal to I into equivalent impedance when capacitors are connected in a series. So the C equivalent we are calculating across source terminals. So what will be the value of C equivalent? If you simplify this, you will get a C1 C2 divided by C1 plus C2. So we are writing this as I of t into 1 by j omega C1 C2 divided by C1 plus C2. So this value of capacitance which you are writing here is called as C equivalent. Okay, so when more than one capacitors are connected in series, then 1 by C equivalent, just take a reverse, 1 by C1 plus 1 by C2 plus so on. That's all. So this is the C equivalent when more than one capacitors are connected in a series. So if only two capacitors are there, then directly you can write C1 C2 by C1 plus C2. Now, what will be the voltage division principle applicable here? So suppose I want to find a voltage on first capacitor. So it will be equal to V1, or it will be a function of time. I should write actually V1. It should be V1 of t, because all are functions of time. So this will be equal to, what is V1 of t? It should be equal to impedance on capacitance. So it is 1 by j omega C1 into I of t. So if you substitute that I of t formula you will get a C2 divided by C1 plus C2 into V of t. Similarly, if you want to find V2 of t, this is the impedance on second capacitor 1 by j omega C2 multiplied by current. So if you substitute the formula for current, you will get a C1 by C1 plus C2 into V of t. That's all. So this is the voltage division principle applicable on capacitors connected in a series. So it is not like resistors and inductors. Be very careful. It is little bit different. Okay. So voltage on capacitor C1 will be C2 by sum of capacitances into input voltage. Similarly, voltage on capacitor C2 will be C1 divided by sum of all the capacitances into input voltage. So this is what you get when you take a voltage division principle applicable on capacitors. Okay, it is little bit different. It is not like R and L connected in series. This is little bit completely different. So be very careful with this case. Okay. Now, what about parallel connections? When will you say that the network elements are connected in a parallel? So here, very important. If two network elements, are connected between the same set of nodes, then the network elements are said to be in parallel. That's all. Simple. If network elements are in series, same current will flow. If network elements are in parallel, same voltage drop will be there. So how will you decide whether the elements are in parallel or not? If they are connected between same set of nodes, very important. I have to identify this carefully. If they are connected between same set of nodes, then the network elements are said to be in parallel. Now, when network elements are in parallel, they have same voltage drop but different currents. They will have same voltage drop but different values of currents. Elements in series, they will have same current but different voltage drop. That is the difference with series elements and parallel elements. Okay. Now, if you take resistors in parallel, resistors in parallel. So I can go ahead with when you are dealing with parallel elements, I told current sources will be considered most of the times, not a condition, but most of the times. I am taking a DC current source, IS. Now, elements are connected in parallel. What is the meaning? These are my two set of nodes. Between these two nodes, I have my network element. And again, between the same set of nodes, I have one more network element. So these network elements are R1 and R2. Now, you can see all these three nodes are connected between same set of nodes. These are the two nodes. Let us assume this is node A and this is node B. So if you have a case where all the network elements are between same set of nodes, then we can say here IS, R1, R2 are always connected in parallel. So let us assume the value of this node voltage is some Vs. So when you write node voltage as Vs, all the branches which are connected between the nodes are having the same voltage. There is no voltage at B. Voltage at B I am assuming as 0 volts. It's a ground node. That is the reason I am writing my node voltage as Vs here. Okay. That means Vs is the drop between your node A and node B. Okay. That means all these three branches, whenever you measure node voltage, is it measured with respect to ground. Upper terminal voltage will be positive, lower terminal voltage will be negative. So at A positive voltage, at B 0, negative terminal will be there. So that's the reason we measure voltage with respect to node. So when you write a representation, this will be plus minus Vs, this will be plus minus same Vs, and this will be also plus minus with same Vs. That's all. So all three branches will share same voltage, but currents will be different. So let the current flowing on the first branch be I1 and let the current flowing on the second branch be I2. Current will always flow from positive to negative. This current source will flow from negative to positive because it's an active source. Okay. Now, what is the KCL or nodal equation at node A? I already told this. Whenever current is coming towards the node, take negative. Whenever the current going away from the node, take positive. Add on the currents and equate it with 0. So what are the values here? Current is coming towards the node, so it is minus Is. Current is going away from the node, plus I1. Again, current is going away from the node, plus I2, equal to 0. That's all. So you are having a Is equal to I1 plus I2. So Is is equal to, what is I1? I1 is the current flowing on resistor R1. So you can write it as Vs by R1. Plus what is I2? Current flowing on resistor R2. You can write voltage by resistance Vs by R2. So you can express this as Vs into R1 plus R2 divided by R1, R2. So what will be the R equivalent seen by the source terminals now? These are your source terminals. So R is nothing but ratio of voltage to current. So it should be Vs by Is. So what will be this value? R1, R2 divided by R1 plus R2. So this is how we are getting two resistors when connected in parallel. We'll have an R equivalent equal to R1, R2 by R1 plus R2. Is it clear? Okay. Right. Is it clear? Just a moment. right? So these are resistors connected in parallel. Okay. Next. Now, what are the currents on each branch? We are saying that current is getting divided. So what is I1? Current on first resistor R1, I am saying as I1, it should be equal to value of voltage V. So I1 must be equal to Vs divided by R1. So it will be Vs by R1. So when you substitute Vs in terms of I, you will get a R2 by R1 plus R2 into I. Similarly, if you want to find I2, I2 is Vs by R2. So when you substitute Vs in terms of I, you will get a R1 by R1 plus R2 into I. So this is nothing but current division principle. How currents will get divided when you take network elements connected in parallel. This is what is called as current division principle. So current division principle on resistors is like voltage division principle on capacitors. So be very careful. If you have a network elements in parallel, you want to find current on any branch, take opposite branch resistance divided by total resistance into total current I. That will give you the currents on resistive branches. Next. Now, if you take inductors in parallel, same logic. I am taking an AC current source and connecting two inductors between the same set of nodes L1 and L2. Let these nodes be node A and node B. Let the value of the voltage at the node be V of t. That means we are saying this as plus minus, this is also plus minus, and this is also plus minus. That's all. All these three branches are connected in parallel. Now let the current flowing on this branch be I1 of t, and let the current flowing on the second inductive branch be I2 of t. Currents will get divided. So this is the current that is coming towards the node. So what is the nodal equation at node A? Nodal equation or KCL at node A. Current coming towards the node is negative, so minus I of t. Current going away from the node is positive, so plus I1 of t. Again plus I2 of t. Equate with 0. That's all. So you will get a I of t equal to I1 of t plus I2 of t. So what is I of t? I1 of t we can express as V of t divided by j omega L1. Current is the ratio of voltage to impedance, plus I2 of t is again V of t divided by j omega L2. So you can express I of t as V of t divided by j omega into, you will get 1 by L1 plus 1 by L2. You can write it as L1 plus L2 divided by L1 L2. So what will be the equivalent inductance when you take two inductors connected in parallel? Therefore, value of L equivalent is ratio of V of t by I of t. So this will be equal to L1 L2 divided by L1 plus L2 without mutual inductance. Remember that. Okay, it is the same logic. Just like two resistors in parallel, R1 R2 by R1 plus R2. Inductors also when connected in parallel, L1 L2 by L1 plus L2. Now what will be current on each branch? I1 of t will be same logic. L2 by L1 plus L2 into I of t, and I2 of t will be L1 divided by N1 plus L2 into I of t. So this is the current division principle that we are applying on inductors connected in parallel. So whenever you have branches in series, we use voltage division principle, and whenever you have branches in parallel, we use a current division principle. That is the main difference. Is it clear? Most of these points you might be knowing. I am just deriving, just to explain these current division rules and voltage division rules. That is more important for me. Okay, right. Next, what will happen if you connect capacitors in parallel? When number of capacitors are connected in parallel, I am taking a same logic, an AC current source with two capacitors in parallel with the source. So let us say C1 and C2. They are connected between the same set of nodes. And let the voltage at node A be V of t. So all these three branches are connected with respect to terminals AB. All these three are in parallel. Now, because this is V of t, this should be plus, minus, plus, minus, plus, minus. All three branches will have same drop. Let the current on first capacitor be I1 of t. Let the current on second capacitor be I2 of t. That's all. Same representation, no change. So if you write a nodal equation at node A, what will be the nodal equation at node A? Again, you will get minus I of t coming towards the node negative, going away from the node positive. So remaining two currents will be positive, equate with 0. So we are getting a I of t equal to I1 of t plus I2 of t. Now, how you can write I1 of t? I1 of t is a current on capacitor ratio of voltage to impedance. So it will be V of t by 1 by j omega C1. So it becomes a j omega C1 into V of t plus again j omega C2 into V of t. Both will remain same. So how you can express this? We can write a I of t equal to V of t into j omega C1 plus C2. So you can express this equivalent impedance V of t divided by I of t as 1 by j omega C1 plus C2. So this is what we call it as equivalent impedance seen by the source terminals. R equivalent and Z equivalent. So from here you calculate C equivalent. So this is just like 1 by j omega C. Therefore, the value of C equivalent when capacitors are connected in parallel is C1 plus C. That's all. Capacitors connected in parallel is like resistors and inductors connected in series. Okay. Now, what will be I1 of t? It will be V of t by 1 by j omega C1. So it becomes j omega C1. So this I1 of t will be, in place of V of t, you can substitute I of t by j omega into C1 plus C2. So j omega will cancel. You will have C1 by C1 plus C2 into I of t. Similarly, I2 of t will be C2 by C1 plus C2 into I of t. That's all. So these are current division principle applicable on capacitors connected in parallel. Current division principle on capacitors is like voltage division principle on resistors and inductors. So you have to keep these points in mind. When you are doing problems, we will be using this directly. So that for that purpose only, I am explaining all these cases. Otherwise, series parallel, there is nothing very much different. Most of the things you might be knowing. So I have taken this to explain these points only. Is it clear? Right. Let me go to the next one. Just a moment. Oh. Right. See this question. Or let us do one thing. Just a moment. I will take one more bit and then we'll see this. Here I will add one more. Yeah. Okay. See this question. I want R equivalent seen across terminals A and B. This is a circuit I am taking. So these are terminals A and B. I want R equivalent seen across this terminal, and this is repeating for infinite times. And all these resistance values are 1 ohm. Standard bit. This came in so many different exams, including ISRO, all these things. Just a moment. Okay. Okay. This is repeating for infinite times. Right. Now, what will be the R equivalent here? Just try to understand this point. Whatever the R equivalent you are seeing across terminals A and B, the same R equivalent you will also get across terminals C and D. These are terminals C and D. You will get the same R equivalent between these two terminals. Okay. Now, that's the reason from here I can see the network right side. This value also will be equal to R equivalent. So how you can simplify this? You can now simplify the circuit as 1 ohm connected with 1 ohm like this, and the remaining entire part of the circuit you can replace it with a single resistance equal to R equivalent. And we are measuring R equivalent seeing across these two terminals. This is your R equivalent from terminals A and B. This is a simplification that you have to carry on. Is it clear? Now, whenever you calculate R equivalent across terminals A and B, this is a very important hint. Try to understand this. Never do the problem from terminals A and B. Come from the opposite side. Solve network from opposite side. Very, very important. Okay. So when you want R equivalent across AB, don't touch those terminals. You come from the opposite end. So opposite end, how are these two branches connected? They are connected between the same set of nodes. That means they are connected in a parallel. So what is R equivalent we can write now? We can write as R equivalent into 1 divided by R equivalent plus 1. So we will have that resistance as R equivalent divided by 1 plus R equivalent. Okay. Now, what is the remaining part of the circuit we have? Again, you are having here as 1 ohm, and these are your terminals A and B, across which we are actually finding a value of R equivalent. That's all. Now, with respect to these terminals A and B, how are these two branches connected? Both these branches are connected in a series. So, what is your R equivalent now? R equivalent can be expressed as equal to, just add these two, 1 plus R equivalent divided by 1 plus R equivalent. So you will get a R equivalent plus R square equivalent equal to 1 plus R equivalent plus R equivalent. So you can express this as R square equivalent, 1 R equivalent will get cancelled, minus R equivalent minus 1 equal to 0. So this is a quadratic equation in R equivalent. Now just find its roots. What will be the value of R equivalent? Therefore, value of R equivalent will be, just take its roots, minus b plus or minus square root of b square minus 4ac by 2a. So minus b means it will become 1 plus or minus square root of b square, 1 minus 4ac. So it becomes 4 plus 1, 5 divided by 2a, 2. So what will be this value? R equivalent will be, resistor will never be negative. Resistor magnitudes are always positive. So take positive values. So how much you will get? Just simplify that. 1 plus root 5 divided by 2. 1 plus root 5 divided by 2. So you will get a 1.61 ohms. 1.618 ohms. That's all. So this will be your R equivalent for this particular case. Is it clear? R value cannot be negative. So take only one root which comes to be positive. Don't take 1 minus root 5 by 2. Take only 1 plus root 5 by 2. That will be your answer. Okay. Now, this is a standard bit. It is there in almost all standard textbooks, and most of the times given in exams directly. Okay. Now, same question. Suppose you are given as like this. Instead of 1 ohm, all resistance values which I am giving happens to be 10 ohms. Then what will happen? If this is the network, then what is R equivalent seen across the terminals A and B? These values are 10 ohms, 10 ohms, 10 ohms. All values are 10 ohms. And this is repeating a infinite number of times. Same question only, it's a part of that. So let us assume this is a part in that particular question. What will be this value? How much you can tell? What will be the answer for this case? Right. Now you can again do the question by using the same model. Whatever R equivalent you are seeing across terminals A and B, the same R equivalent will be also there across terminals C and D. Repeat the same problem, you will get the answer. But instead of doing that, make use of the linearity property and homogeneity property. Which property you can use here? You can use homogeneity property. Because you know that resistors are linear elements. That means they obey the principle of additivity as well as homogeneity. So if you multiply each resistor with a constant K, which is 10, then the R equivalent also will get multiplied by the same value 10. That means when you have calculated the problem with 1 ohm, we get R equivalent as 1.618 ohms. Correct? Now, if you are calculating the same problem without any change with 10 ohms, that means you have multiplied the resistance with a constant which is equal to 10. Then the R equivalent which you get will also get multiplied with the same constant equal to 10. That is what is homogeneity property. So this will be equal to 16.18 ohms. That's all. This will be your answer. Finish. So this is how you can use the homogeneity property and get the response. Instead of doing all this, easily you can map this. Is it clear? Okay. Now, let us see what is given in the next problem. Is it clear? Should we do one more case based on this logic? Just a moment. Just hold on 1 minute, 1 second. Yeah. Suppose if I give you one more bit on the same question, let us assume it is B bit. A bit already we have seen, standard one, then 10 ohms. Now I am taking one more case where first resistance I am taking as 5 ohms and all the remaining resistors I am taking as 10 ohms. Now what will be the answer? This is the case. And this is repeating infinite number of times. What is the R equivalent seen across the terminals A and B? What will be this value? What will happen to this value? It's a question given in one of the ISRO paper. Yeah, I have this paper here. Yes, correct only. It's one of the paper from ISRO, question from ISRO paper. There is nothing very tough here. You use a standard concept. Don't try to remember answers. For 1 ohm, you remember 1.618. For 10 ohms, you remember 16.18. Then try to apply that concept here. You can do. I'm not saying it is wrong. But this type of process becomes very big hurdle, because when you are going for exams, at least 8-9 subjects will be there in your head. So there is no point that this answer will suddenly come into your brain. It may come with a different value. So automatically you will go for a wrong choice. Procedure is very important. Now use a symmetry in these type of questions. So what is this symmetry logic? Just now we have used the same thing. I am using the same thing again. What I am doing is I am drawing the same circuit like this. 5 ohms. This is 10 ohms. Now whatever the 10 ohms he has given, I am keeping two 5 ohm resistors in series. And again this 10 ohms. And again 10 ohms. And this is repeating for infinite times. So these are my terminals A and B, on which I am calculating the value of R equivalent. This is the circuit. Okay. Now what happened? See, what is your basic circuit now? Whatever you are having here, this 5 and 5, because I have connected them in series like this 10 ohms also I will do like that only. Don't think I am keeping 10 ohms here. This also we will separate them into resistors of 2 5 ohms which are connected in series. So it will look like this: 5 ohms, 5 ohms, and this is going for infinite number of times, infinite times. Okay. Now this 5 ohms, 10 ohms, and 5 ohms is forming the basic part of the circuit. And whatever the R equivalent you are measuring from this, again the same R equivalent will come when you are measuring across the terminals C and D. The same value will come whatever you measure across these terminals C and D. So this is my terminal C. Okay. Now what is my circuit now? Now how I can replace my circuit elements? So I have 5 ohms resistor, 10 ohms resistor, one more 5 ohms resistor. This is the basic part of the circuit. And then I am replacing the remaining part of the circuit by single resistance which is equal to R equivalent. And these are my terminals A and B. So I want to measure R equivalent seen from these terminals A and B. So what will be my value of R equivalent? Come from the opposite end. Don't start from terminal AB. Come from the opposite side. So this 5 and R are connected in series. So I am writing R equivalent plus 5. And this combination, whatever it is there, is connected in parallel with 10. So it will be, because you can see these two branches are between one node, and the sum of these two branches are coming between the same node. That means this 5 and R equivalent which are in series is coming in parallel with 10. So it should be multiplication divided by sum of these values. So it becomes a 15 plus R equivalent. And whatever the combination you got, the resultant is again in series with 5. That's all. Okay. Is it clear? 5 and R equivalent are in series because same current will flow on these branches. Then the combination is coming between the same set of nodes here. So they are in parallel. Now the result again comes in series with this 5 ohms. So that should be equal to your R equivalent. So what will be this value? 15 R equivalent plus R square equivalent equal to 50 plus 10 R equivalent plus 75 plus 5 R equivalent. So this 15 R equivalent, both sides will get cancelled. So you will have your R equivalent, only positive value will come, root over 125. So you can write it as 5 root 5 ohms. That's all. So if you want to write it as the correct value, 5 into root 5. So it becomes 11.18 ohms. That's all. This will be your final answer. So this is how you have to make use of this symmetry. If you make use symmetry, then confusion will not be there. There is no need for you to memorize. All these 3 bits I have asked in different exams. First one is standard bit. You can see this in any standard textbook. Remaining bits which we have done, the one with all 10 ohms resistor and the one with 5 and 10 ohms resistor. This is 2 bits coming from the same area. So this is how easily you can find the values of R equivalents. Okay, we'll see a lot many questions on calculation of R equivalents in tomorrow's class also. Today, my important aim is to cover current division and voltage division principle. That must be clear. And whenever you calculate R equivalent from any two terminals, don't touch the terminals. Start calculating from the opposite terminals. Okay, so here I want across AB. So I did not touch 5 ohms first. I came from the opposite side. That is the very important clue. Never touch the terminals on which you want to find R equivalent. You are disturbing the circuit. Don't do that. Go into the opposite side of the circuit and then come to your side. So you can easily observe which are connected in series and which are connected in parallel. So that is a logic which will be very useful. Resistance values are never negative. Okay. So Don't take any negative value, take the root which comes out to be positive. Is it clear? Okay, right. So these are questions for the day. Just a moment, let me save it, the file once. I hope things are clear. Fundamentals are most important in this subject. Then any type of question you can easily do. Series, parallel, that how they are coming, it is must. That you have to be very clear. Then network elements, if you identify correctly, numericals you can get in very quick time. Right. Let us go to these questions. Yes, Prasanna. I am unable to get your voice.
Sir, no doubts, sir.
Sivaram?
Sir, no doubts.
No doubts. Okay, right. Thank you. I don't know why it is going like this. Let us see. Yes.
Hello?
Yeah, tell me.
So yesterday we did one question in which there was inductor with internal resistance and internal resistance.
Yeah, tell me.
So in that graph of IT versus T was given, and we have to find the E absorbed, energy absorbed. So the formula of energy absorbed is integration of I square R dt, where R is 1, so integration of I square dt.
Yes.
So can we just square this graph and find the area?
You can find, but squaring graph becomes easier when it is a square waveform. But if you are given ramp function or any other functions with the equation format, you cannot do that square, no? It becomes a little difficult.
Quadrilateral, starting it is increasing by 3 slope.
Yeah, you can do that procedure. There is nothing wrong. What you are saying is correct only. You can do.
But answer, I could not conclude to answer.
Yeah, it's up to you. If you want to do like that, you can do. You'll get the same answer. You can square it and then take its area.
I'm not getting the same answer.
You should get that because the procedure is same. Maybe you might have done somewhere a little bit wrong, or just check once more your solution. You will get the same thing.
Means if the maximum value is given 6, then I have to just do is 36 and the slope we will just integrate it.
No, that is wrong. You cannot take a coordinate and square it. You have to take slope line equation and then square the line equation.
Oh, we have to square the line equation.
Because that is what you are doing now. If it is step waveform, no problem. You square the amplitude, you will get it. Like step voltage of 5 volts is there. Square will be 25 volts. That's all. But if it is line equation like T, square means it becomes T square.
Okay. Means
You cannot square you cannot square amplitude for ramp waveforms. You have to take line equation and square it.
Okay.
Right. Okay.
Sir, I have one more doubt.
Tell me.
Sir, when we say it's about Thevenin's equivalent. Hello?
Yeah, tell me.
So if we do Thevenin's equivalent across any load, then the current will change.
What is that? Equivalent across which branch?
So in a question, there was 3 resistors in parallel. With voltage source with some internal resistance. I'm getting it.
No, if you have any question, I could not get your question correctly. If possible, you post it. We will see that explanation. Currents will get divided when you have them in parallel.
post it with my solution. You just rectify and do that.
Okay, right.
Hello.
Yeah. Who is this?
Good evening, sir. This is Shweta.
Yeah. Tell me.
So, I have a doubt in the first lecture, actually.
Yeah, which one?
So, when we are studying the cases of inductor, what happens to it? There's one case that says when T is greater than 0, the inductor is replaced by a current source as well as the inductor itself.
Yes. In parallel.
How is that? Yes, sir. How is that happening? I don't get it.
See, that I will give you a clarity when we start tangents, because that's the reason I told, whenever you take any branch, if you want to connect it with current, you should be connecting it in parallel. So that's the rule which we use here. How you will get that exact explanation is, you take the Laplace equivalent and normal KCL equivalent, both will satisfy. That's the reason we connect them in parallel. For the capacitor, we connect the voltage source in series.
No, the parallel part I understood, but how when it is T equal 0 plus, then
No, it is T greater than 0 only.
No, sir, I'm getting there. When it says T equals 0 plus, then only the current source is there.
Yes,
that I
yes.
got. But how is it replaced with the current source in also the inductor in T greater than 0?
Okay, I'll explain. Just see this. So whenever some sudden changes happen in the circuit, inductor does not
Yes,
allow change in current. So that's the reason we are replacing with open circuit, right? Up to
Yes.
that it is clear at 0 plus.
Yes, sir. Yes,
Now,
sir.
after 0 plus means you have given little time. By that time, what happens is resistor actions will keep starting. So there will be some flow of currents and distributions taking place after 0 plus. Then your inductor will start charging or discharging once again. That is the reason we are showing inductor after switching action, T greater than 0. That is the meaning there. Is it clear now?
Okay.
Okay.
And so when is exactly the settling time happening? Because when, according to this case, when T is greater than 0, we should take inductor as well as a current source with it. But in solving the inductor problem, we didn't take the current source with it when we were calculating.
In steady state. See, when you are drawing the network in steady state means after settling time. Once your TS starts, right? At that point of time, this current source which you are representing is actually stored value of the current on inductor.
Yes,
that
sir.
is not actually current source. We are representing it as a current source. It is actually stored value of the current. So that current will be dissipated on remaining elements present in the network.
But when before the settling time, when the question that we do, what is the amount of time taken by the inductor to reach steady state? It's not there yet. Then
it's not there means you will get as a function of time. Then you have to consider T greater than 0 circuit only. So whatever you get the response is a function of time. Current inductor current as a function of time.
So, but when we drew the circuit in the question, we didn't draw current source along with it. Why didn't we do it?
I am drawing the circuit in steady state then. That's the reason I did not draw.
So, but it's not in the steady state yet now.
No, when you are taking a circuit as T tends to infinite, means after settling time, it reaches steady state only.
So after settling state that I got, but settling time, when we have to calculate settling time, then we don't take the current source.
Because there is no current source, no? There is no initial value of the current on inductor at that time.
Okay.
For when you are immediately switching at 0 plus, there is no current, stored value of the current. So you need not show anything.
Okay.
That current will come after steady state has reached, and again you are opening the switch to remove your source. Then that will come.
Come again? Sorry.
That current source, whatever you are representing in parallel with inductor, when you are representing that, when I have again opened the switch for removing of my source, last part of the question, we have removed the source.
Yes, sir.
At that time only we are showing this. Then again you have to show this. Otherwise, initially when you are drawing the circuit after 0 plus, there is no
Yes, sir.
initial value of the current on inductor. So you need not keep anything in parallel.
Okay. Okay. Got it, sir. Thank you so much.
Yeah, yeah, okay, fine. Bye.
Hello, sir.
Yeah, yeah, hello, tell me.
Sir, I have a doubt in first class, sir.
Yeah,
Sir, I have a doubt that why we are taking steady state equal to t equals 0 minus, sir.
See, t equal to 0 minus is a time instant where you are about to start your switching action, right? Switching action is actually taking place at 0. So just before that, all the elements in the circuit are in saturated state only. Suppose just take one simple example. You want to switch on a fan. Hello?
Yes, sir.
You are going to switch on a fan. Now, just before switching on the fan, is the fan in steady state or not?
Yes, sir, it is off. Okay.
That is what is called as a steady state, 0 minus. There is no energy on that, but fan is stable. So that is what is meant by steady state. Just after you switch on the fan, what will happen? Slowly it increases its speed, right? After some time, it reaches to a constant speed. That constant speed is again steady state. So there are two steady states: before switching on the fan, after some time switching on the fan. So these two are like a 0 minus and t tends to infinite. Immediately after switching action, what is present is transient state.
Okay, okay. But after after in transient state also you took t equals 0 plus equal to t equals 0 minus, no, sir, in current, for current.
Yes, yes, that will be there, because that will happen only on inductor and capacitors, not on resistors.
Okay, okay, sir. Why it will happen, sir?
Because they don't allow changes. That is what I have proved with that integral part. Now, that second part of the integral is 0. Because they don't allow changes in current or voltages. Sudden change in currents.
Okay, okay, sir.
Okay?
Okay. Okay,
Right.
sir. Okay, sir. Thank you, sir.
Yeah. Yes, any more?
Hello, sir.
Yeah, yeah, tell me.
Sir, today's ISRO question, no, sir.
Uh-huh.
Sir, can you please explain after we find I1 of t?
No, which part of the question you want me to explain? Current?
Yes, sir. We found I1 of t is equal to 0.5 into 1 minus e raised to minus 2t.
You got that expression, right?
Yeah, sir.
Now
But
what he is asking is, in that time expression I1 of t, you take some value of time t equal to t1. Okay, at that
Yes,
point of time, the current has to be 63% of final value. So what is the final value in that I1 of t expression you got? You substitute t equal to infinite. What is the final value, 0.5 or not?
yes,
So
sir.
that is the reason what I am doing is 63% of 1 by 2 means 0.63 by 2. That's all.
Okay, sir.
Got it?
Yes, sir.
Okay, right.
Sir, good evening.
Yeah, good evening. Please tell.
This is Agnesh Vaidya.
Yeah, tell
Sir,
me.
sir, I have the doubt in the second class, sir. Sir, when you said R is always a passive element, no, sir?
Yes.
It acts as a passive, or is it a passive element?
It is passive only, 100% passive.
The passive element. Sir, you told one question, sir. When will be the voltage and the current will be passive, sir? That I did not written that.
Which one? Just repeat.
Sir, you said that R is always a passive element.
Okay.
And you said some note that you said one question that you raised a doubt, sir. When will be the voltage and current will be passive?
Okay. Your doubt is to check whether the element is active or passive, right?
Yes, sir. My doubt is that when the in which time the voltage and current will be passive element, acts as passive.
See, it is not with respect to time. You got some values of voltage and current, okay? Some
Okay,
values.
sir.
So you multiply those two values. If the magnitude is positive, then element is passive. Power values, whenever power values are positive, that means that element is absorbing power. So it is passive.
Okay, sir. Then
If power values are negative, then the element is delivering power. Hence it becomes active.
right, sir. Clarify.
Okay, right.
Sir, one more doubt, sir.
Huh.
Sir, here you said no, sir. Internal resistance in ideal and practical voltage. Sir, what should be the internal resistance in ideal and practical voltage, sir? And I have written a question in.
No, ideal voltage source internal resistance should be 0.
Ideal voltage source? Sir?
Internal resistance is always 0.
Okay, sir.
But practical voltage sources internal resistance will be there, but its value should be as small as possible.
Okay, sir. For voltage it is 0. For in ideal voltage, sir, please.
Ideal voltage source internal resistance is 0.
Okay, sir.
Practical voltage source internal resistance should be finite. It should be a small value.
Okay, sir.
Okay. Yeah.
Thank you, sir. Perfect.
Yeah.
Hello, good evening, sir.
Yeah, good evening. Tell me.
In yesterday's problem, we found energy absorbed in the inductor, no, sir.
Okay, right.
In up to first 6 seconds.
Uh-huh.
There we found we only calculated for resistor, and for inductor we said positive slope, negative slope will get cancelled, and we didn't found.
Yes.
If we found up to 4 seconds only.
If you want to find up to 4 seconds, okay.
Yes, sir. Then we have to consider inductor absorbed power, no, sir.
Correct. You have to consider. See what happens. Just a second. If you want to calculate up to 4 seconds, that means your graph is having a positive ramp from 0 to 2 and a constant slope from 2 to 4, right?
Yes, sir.
So your resistor values will be same. That 24 and 72 something what we got, that remains same. There is no change. Inductor, what you do, you calculate the energy absorbed by the inductor up to 2 seconds. So it will be half L. What is the current at 2 seconds? It is 6 amps.
Sir, okay.
Okay, correct.
I thought that the formula.
No need to take. Same thing.
Is stored, no, sir.
Stored or absorbed energies is same only, no.
Okay. Sir.
Inductor will absorb and will then store it up to 2 seconds. But after 2 seconds, it is what it is doing. 2 to 4 seconds, it is not storing energy. It is not at all doing any work. Current has been saturated. So it will not absorb nor deliver. So in that range, energy absorbed will be 0.
Okay, sir.
And in the third region, it is delivering. That's the reason we got negative value.
Okay, sir.
So if you want to calculate only up to 4, take resistor values, add them. Inductor value, take only up to 2 and add with the net result. You will get the answer. That's all.
Okay, sir. Thank you, sir. I understood now.
Okay, right.
Hello, sir.
Yeah, tell me.
Hello, sir. I have doubt in sir finding the circuit element.
Finding
the circuit element, sir, whether it is inductor or capacitor.
Okay, today's class, whatever the thing which you have done.
Yes. Sir, in that, if it had given, sir, both are ramp function, then what we will do, sir?
Resistor. Both are ramp functions means resistor.
Hmm.
Because both are ramps, there is no integral, there is no derivative. So obviously it should be multiplied by some constant. So definitely it will be resistor. That's all.
Okay, sir. Okay, sir. Thank you, sir.
Yeah.
Hello.
Yeah, tell me.
Good evening, sir.
Yeah, good evening.
Sir, yesterday we did a problem in RC circuit, sir.
Mm.
In that we have drawn 2 circuits to find out settling time, right, sir?
Yeah.
There we have taken settling time is equals to 1% of 5C of t, no, sir?
Yeah.
Sir, how did we get that, sir?
That is a definition on settling time.
Okay, sir.
Whenever you have decaying exponentials,
okay,
you have to take 1% of initial value because you will have maximum value at 0 plus. So you take 1% of that initial value.
Okay, sir.
If you are taking a increasing exponential, like voltage function which you got might be increasing function, exponentially
Yes.
increasing. For that case, you take 99% of final value. Both
Okay.
are same. You will get the same values.
Yes, sir. Thank you, sir.
Okay, right.
Hello, good afternoon, sir.
Yeah, good afternoon. Tell me.
Sir, I had a query means like yesterday for the current through capacitor, you told no that for t greater than settling time E equals to minus t by 5 ampere. We got, sir, one question. Sir, you told that in books it is given e to the power minus t minus ts by 5. Sir, how both are same, sir?
No, you are writing as a expression as a function of time for t greater than ts. Okay.
Yes.
If you write u of t minus ts, what is meant by u of t minus ts? It is nothing but a step function defined for values of t greater than ts, right?
Yes, sir. Yes, sir.
So the same expression we are defining in mathematically in terms of equation, we write as t greater than 0. If you want to write in your signal format, you write as u of t minus ts. That's all.
Okay, sir. That means that e to the power t minus ts that will not affect, sir. Means
Wherever t is there. If you are writing for t greater than ts, if you want to represent in signals format, wherever t is there, you replace it with t minus ts. That's all.
Okay, sir. Okay. Got it, sir. Got it. Thank you, sir. Thank you.
Right. Okay. See.
Hello, sir.
Yeah, tell me.
Sir, today's class dependent sources, sir.
Your voice is not clear. Just.
Hello.
I'm not getting it. Please check it once.
Today's class.
Yeah.
Dependent sources. Can you explain, sir?
Dependent sources, their value, whether it is voltage or current, is going to depend on response across any other branch present in the circuit. Suppose you take voltage controlled voltage source.
Yes, sir.
Teluga?
Sir.
ఇప్పుడు వోల్టేజ్ కంట్రోల్ వోల్టేజ్ సోర్స్ ఉందనుకో అంటే దాని అర్థం ఏంటి మనం తీసుకుంటుంది వోల్టేజ్ సోర్స్ మనం ఏం చెప్తున్నాం వోల్టేజ్ కంట్రోల్డ్ వోల్టేజ్ సోర్స్ అంటున్నాం అంటే తీసుకుంటుంది వోల్టేజ్ సోర్స్ దీని మ్యాగ్నిట్యూడ్ వోల్టేజ్ ద్వారా కంట్రోల్ అవుతుంది ఏ వోల్టేజ్ మన నెట్వర్క్ లో ఏదో ఒక బ్రాంచ్ అది రెసిస్టర్ అవ్వచ్చు ఇండక్టర్ అవ్వచ్చు కెపాసిటర్ అవ్వచ్చు ఏదో ఒక బ్రాంచ్ ఉండొచ్చు ఆ బ్రాంచ్ మీద వోల్టేజ్ ఎంతైతే ఉందో ఆ బ్రాంచ్ వోల్టేజ్ ఈ డిపెండెంట్ సోర్స్ ని కంట్రోల్ చేస్తుంది
ఓకే సార్ థాంక్యూ సార్